Is that okay, Damien?
Yeah, it's fine. Yeah.
Okay. I mean recording it. Is it okay?
Yeah, of course. Yeah, yeah, sure. Yeah.
Okay.
Okay, so let me start. Hello everyone, it's my honor to introduce Dr. Damien Teney. He's a part of the University of Adelaide before, and especially the Australian Institute of Machine Learning. And he's about to join the IDEAP Research Lab in Martigny, Switzerland. He was previously affiliated with Carnegie Mellon, University of Bath, and University of Innsbruck. He has received his PhD in computer science at the University of Rijeka, Belgium, and was advised by Justus Pieter. His research interests are at the intersection of computer vision and machine learning. Interestingly, he was part of the team that won the VQA 2017 challenge and proposed the use of localized faster RCNN object features, also known as bottom-up and top-down attention for vision and language tasks, which has in a way revolutionized vision and language research and is still being used for the state-of-the-art systems, including the current transformer-based systems. So with no delay, I yield the stage to Dr. Tim.
Yeah, thank you for the introduction. It's my pleasure to be here. It's too bad we cannot do this in person. It would be a nice time of the year to visit Phoenix. Anyway, we'll do our best. So I'm really glad to be speaking today. So I'm going to be talking about visual question answering. And as you know, the field of visual question answering has really seen a ton of progress over the past few years. And it's been a catalyst for a lot of interesting developments in vision and language. And today I want to take a step back and reflect on the state of the art. So the task is obviously a very complex one, very ambitious one. And I think that's what was the initial appeal for the task. It's just the fact that it was so ambitious. And we had some big aspirations. I give you here some examples that you've probably seen before from the VQA V2 dataset. And those questions are very complex. They require a lot of things from computer vision and language processing. And just the learning aspect is extremely ambitious. And I think the complexity actually really jumps at you if you look for training examples in the kind of data set that we use. So here I picked one for the last one about the banana mustache. I looked for training examples, a data set that could support the learning of the concepts that are required. So I looked for questions about bananas and questions about mustaches. And if you look at them, you see there's some connections, but learning from those few examples, and there are a few more, but it's just the same kind of things, just a handful of them. Learning from them to answer this kind of questions is obviously a big challenge. And there are some non-challenges that have been addressed and actively studied, like having a long tail of answers, the issues of dataset biases, shortcut learning, and all that. So I don't want to rehash any of those challenges in particular, but I want to look at the bigger picture and actually ask what is achievable today in VQA with the tools of machine learning. So I think one of the central challenges is really what we call strong generalization. So that's also called out-of-domain generalization or out-of-distribution generalization. So that's really the fact of learning about concepts in a certain setting in the training examples and applying those concepts in other settings, so in a different distribution. And this is kind of a central challenge for machine learning in general. And the thing is that it hasn't been demonstrated, not even on toy data, and let alone on VQA or any of those complex tasks. So what I've proposed to do today is to use the lens of causal reasoning. And I think that's going to be interesting because it allows to pinpoint some limits, fundamental limits, not really of deep learning in particular, but of statistical learning in general. And the point is that the kind of learning by association that we do with statistical learning is not sufficient for strong generalization. And there's really a fundamental limit of what you can learn from a set of IID training examples. And it doesn't matter how many of them you have, no matter how large the data set. So for those who are not familiar with causal reasoning, and some of you are already, but the others might wonder wonder if the causal reasoning is actually necessary to do machine learning. I would argue that it's not. It's not in the sense that thinking about, say, information theory or algorithmic complexity is also not necessary. But the causal reasoning principles are really interesting because they can provide a new layer of understanding of existing methods, and they can also point at directions on how to develop new methods. So if you have questions, I see there's a question in the chat about the audio. I don't know if...
Yeah, it's clear now. So it was a bit choppy at a bit, but now it's clear.
Okay, I guess it's the connections. Yeah, well, let me know if there's anything you think I could do. Yeah. And if you have questions during the talk, feel free to jump in. I'll try to have a look on the chat, but otherwise, you can feel free to use the audio to interrupt also. That's fine. So in this talk, yeah, one more thing about causal reasoning. I think it's interesting. Well, you might wonder why this focus on causal reasoning is kind of emerging these days. There are some interesting papers that have come out recently. I give you some references down here. One of them actually is very timely. It came out last week on Archive, just as I was preparing this talk, so I figured that's a perfect review paper. So if you're interested, that's a great one to check out. And so you might wonder why machine learning has been so successful so far without any considerations about causality. And I would again argue that it's because we are looking at very complex tasks and tasks that are more and more complex. When we did some things like image recognition on ImageNet, I think those tasks were associative by nature. For example, in ImageNet, the images are cropped around one object, and there are not many distractors and not many features that could be spuriously correlated with the labels. So I think the aspect of OOD generalization and causal reasoning become more and more important because we look at more and more complex tasks. So in this talk, I will first review some causal principles. Most of you are familiar with these, and for the others, I hope that this will give you just enough flavor of how interesting those concepts are. And then I will see how that applies to the evaluation of VQA models and how they can help us in building better VQA models. So causal reasoning, that's basically an extension of probabilistic inference. And the key thing is that with causal reasoning, we reason about interventions. And interventions, that's basically the kind of acting on the world that we can do. So I'm going to illustrate that with a concrete example. Let's say we have a task in which we want to predict the car's top speed from an image. So we have a training set of images of cars. So I give you some examples here. And those cars, well, those images have been annotated with the top speed of those cars. And you have a lot of different cars. And the point is that here the data set is kind of biased in the sense that some specific cars like Italian Ferraris that are mostly red, are very fast usually. And sedan cars are not as fast usually. So that's the kind of bias that we can expect from natural distribution of training data. And so if we learn a statistical model on this data, so the kind of traditional machine learning model, we're gonna learn correlations basically. In this model on this biased data, we learn things that are just like red means fast. And that's obviously not correct. It's kind of correct on this kind of data, but it's not going to apply in the real world. There's nothing that tells you any relations. Well, there's no mechanism in the real world between the paint of the car and the speed of the car. And so this model is going to be reliable if you have test data with the same distribution as this. If you have only red fast cars and slow white cars in the test data, that's fine. You can have some high accuracy. The difference with a causal model is that then you can do better on OOD test data. So test data that really like those two examples where you have a wreck that's so rusty that it's actually red, and like this kind of Ferrari that you would seem to buy that's with the golden paint. And with a causal model, you learn the effect of interventions. So interventions, that mean you learn what would happen if you were to act on the world. Say you would repaint a car. So if you have this, this blue Peugeot here, if you were to repaint it, you would learn that the speed of the car is not going to change. So the difference on the left is that the statistical model learn a conditional distribution, and the causal model on the right learn the distribution of the speed, but based on the do operator. That means that you do an intervention on the variable of the color. So those two things are very different. And so the key thing is that once you have this kind of causal model, then you can do some predictions in situations that have not been seen in the training data. And so another point that's really important is that having more data does not make the statistical model better in this sense. So if you have more data of the same distribution, that is, say, more red Ferraris, it still doesn't help you distinguish what is the causal principle, causal mechanism in this data, and what is the spurious correlation. So it doesn't matter how much data you have, you're still limited by being constrained by the distribution of the data that might have some selection biases or other annotation artifacts and so on. So the question that arises then is, can we learn a causal model? So like I said, machine learning is about learning statistical models. And so the other kind, the causal model, how can we learn that? So the basic principle in causal reasoning is that we model the world as a what we call a data generating process. So that represents, it's actually a causal abstraction of the world. It's not an accurate physical description, but how we represent the causal mechanisms in the world that are relevant for our task. And so let's take VQA because that's what we're interested in here. And in VQA, the real process that we actually want to mimic is a human, an annotator that would take a question and an image and reason about it to produce an answer. So that's actually what we are interested in, the real world process that we're interested in. And so this data generating process, what's at the core of it is a causal structure. And we represent that with a causal Bayesian graph. So that's just a Bayesian graph in which we only draw rows between variables that are causally related. So I'm not going to give formal definitions, but that's pretty much what you would expect intuitively. And for the case of VQA, you have here, so again, there's some task-dependent granularity and choices that you could make into what is a relevant causal variable and all that. But as an example here for VQA, I can define the image and the question being two input variables. And then the annotator would extract some relevant visual features, that the V here. And then out of that, and with the question, come up with a correct answer. And on this graph, so this is a Bayesian graph. And so this graph implies a factorization of the distribution. So you have a distribution, the joint distribution over those four variables. The graph implies factorization, we call it causal factorization, which is interesting because now we have the mechanisms. So it's not an arbitrary factorization because the mechanisms are those that will apply at this time. The mechanisms that are independent from one another and that will still apply whatever the distribution of images or questions are. So the mechanism that extract the relevant visual features from the image in the question, for example, should be the same, whatever the distribution of images or questions are. So that's the difference with an arbitrary statistical model or an arbitrary factorization of the joint distribution. So that's for the real world. And so on the other side, we have the model that we want to learn. And so the model, we want it to mimic the real world. So we want to basically mimic the annotator, the cognitive process of the annotator into our model. And so this, this model also Sorry? Oh yeah, that's the eye in the image. That's in the diagram. That's the image. Yeah, the input image. And so on the right, we have the model that we want to learn. And this model also has a causal structure in the sense that it takes some input and produces an output. And what's happening in the model, we can also draw a causal structure, what's being used and what goes into what. And the point is that it's not necessarily the same as the one in the real world. We would like to make it the same, but it doesn't have to be. And for example, you have a VQA model that is badly biased in the sense that it uses only the question. It doesn't use the image at all. You could have this very simplified graph with only the question and the answer as the two variables. Or if you have a VQA model that doesn't use some attention mechanism, doesn't actually extract relevant visual features, but uses the whole image, you don't need the V variable. So you can have this also simplified graph on the right. But ideally, we would like to make the model mirror the real world. We would like the two causal structures to be the same. And so why is this hard? And that's what I mentioned already previously, is that the information is not necessarily in the data. And actually, the kind of data that we use in machine learning in general, which is a training set of examples that are ID, those examples, they don't contain the information about the causal structure of the data generating process. So once you take the joint distribution and you take ID samples of the joint distribution, you lose the information about the causal structure behind the joint distribution. That's really a fundamental principle, and that means that you cannot recover the causal structure just from a set of ID examples. So we'll see later what we can use, but this kind of data is just not sufficient. So before we get there, we'll see first how this can help into the evaluation of VQA models. And I will show you, interestingly, how they can explain some existing data sets and existing principles that people have come up without the causal justification, but now we can have a new vision, a new layer of understanding of those principles. So what we're interested in really is to check whether a model that we have has learned the task of interest. So typically in machine learning, we do in-domain evaluation. And the in-domain evaluation, they're just using a test set from the same distribution as the training data. And what we do is just compare the outputs from the real world and from the model. And we do this in a precise set of conditions that is in the distribution of the questions that have been produced by the annotators. So the very fixed distribution of questions and answers. And so the limitation here is that it cannot tell whether the model really solves the task or if it merely relies on shortcut learning by exploiting dataset biases and such. So it's a well-known problem. And what we really care about is the out-of-distribution generalization or out-of-domain generalization. And that's checking whether the model can learn, can answer any question about a scene, including scenes that are unusual with unusual combinations of objects and so on. And so here we do mostly in-domain evaluation and out-of-domain evaluation as kind of an extra. But the thing is that the former is necessary, but it's not sufficient. So the good models that generalize OOD are just a subset and a small subset of the models that generalize in domain. So the former, the kind of in-domain evaluation that we do is not even necessary if we have a good OOD test practice. So what we want to do is really to check whether the causal structure that I showed in the previous slides between the two sides, between the world and the model, are the same. And so we show that some existing practices like benchmarks like USCP that have OOD test set, they can be explained and justified from a causal perspective. And before we do that, just one more core concept in causal reasoning. That's what's called the ladder of causation. So some of you are familiar with it. It was proposed by Julia Pearl in his book, The Book of Why. And that's ladder with 3 layers. And it's basically a hierarchy of questions that you can ask to a model, a causal model. So there are three layers from the bottom to top. And the first layer is questions that are associative. So it's a kind of evaluation that we do in classical machine learning. So we ask, basically, we pose a set of conditions and we ask what are the likely outcomes that are associated with the input. So that's basically observations, associations, and that's something that's achievable with classical machine learning, and that's what we do with the standard test set like VQAV1 or GQA. But what's more interesting is the layers 2 and 3. So layer 2 is interventions. So this is about intervening on the world and checking the outcome. So that's what we do with data sets that have different distribution between the training and testing. Basically with VQACP, we do an intervention on the data jointing process, and we intervene on the variable that are here, the question type and the answer. So this intervention serves to modify the distribution, the joint distribution of observed variables. And then the third layer in this hierarchy, that's counterfactuals. And counterfactuals, that's basically examples that are similar in many ways, but with a different outcome. And so this corresponds to what we have, for example, in VQFV2, where we have balance pairs. So we have questions, one question with typically 2 images that give different answers. So there have been other papers that propose to do that. For example, in NLP, it's getting more and more popular. So here again, we have examples that are very similar with a different label. And intuitively, that serves to evaluate the behavior of the model very close to the decision boundary, or what should be the decision boundary. And so those 3 types of evaluation, they correspond to 3 different types of queries that we can make to a causal model. And the key here is that every level in this hierarchy is more complex in the sense that it requires strictly more causal information. So each layer is more complex. So if you can do something at layer 3, you can also do, you can also answer queries at level 2 and level 1. But if you have a model that is only learning by association, like the standard machine learning model at level 1, then you cannot do, you cannot answer questions reliably at level 2 and level 3. So now we're going to see how this can help into building better VQA models or understand existing methods for VQA. And I'm going to stick a little bit more with this causal hierarchy. And a key principle here is that learning a model that is capable of answering queries at a given level requires data that matches this level or a level above. So what does this mean? For example, so I presented this 2 sides already, the real world on one side and then what it produces, the data that it produces. For the first level, the data is just a set of ID examples from the joint distribution. So like I said before, it's just a standard kind of training data that we use in machine learning. So that's basically observational data. That's limited, that's level 1. But what we can have also is data from level 2. And so in this case, we do an intervention of the world. So we do some kind of action that modifies the mechanisms. So we set, for example, decide what the distribution of questions should be, or what the distribution of answers should be, or distribution of images should be. And then we get the different distribution of the different samples from a joint distribution. And that's what's called interventional data. And that's used, for example, when we have multiple data sets or data sets that have been collected in multiple settings, multiple environments. So that's for level 2. And now level 3, that's the kind of counterfactual examples, where we have sets of examples that differ only slightly or have different levels. And so the point here is that since you need data from a certain level to answer queries from that level, it means that the levels 2 and 3, which are the levels we really care about if we want to do OOD generalization, those levels are not possible if you have only data from level 1. I think that's really the key here. If there's something to remember, that's really the point, that we need more than just the standard training data sets that we have to do the kind of generalization that we actually care about. And so this is useful because now it can explain why some existing methods can be working from a causal perspective, or also why some methods just cannot be working. So I'm going to give you 3 examples. The first one is a very prominent one. It's basically data augmentations. And data augmentations, I will show you that it's actually simulating interventions. In the sense that it's providing information from level 2. So as you all know, augmentation is basically hard coding and transformation of training examples into additional valid examples. And then we can just use them as extra training data. There might be other ways to use this data, but that's just the way it is. And we can show that this is already providing a lot more information than the initial training examples. And so the causal perspective here is that we, by doing those transformations, we simulate an intervention on a hidden variable that is the causal parent of the data in the data tracking process. So for example, if we augment images with color variations or geometric transformations like flips and rotations, all that, it's the same in principle as intervening on a causal variable that represents the parameters of the camera. And for the questions, if we do something like adding rephrasings of questions, it's as if we were intervening on the writing style of the annotator inputting those questions. And so what we do then is that we get samples, since usually we do stochastic data augmentations, we sample training examples from the modified joint distribution that is given by those interventions. And so we get additional, basically additional samples from this alternative distribution. And this provides information about the causal mechanism independently from the marginal of the data that might be biased in the original data set. And so now we can pinpoint the root source of the improvements of those this practice is really in the knowledge that is put in the specification of the augmentations of the invariances over the joint space of X and Y that are valid for the task. I think this is some principles that are well known or intuitively well known, and the causal perspective gives another layer of understanding of those principles. So I see some questions in the chat. Let me check. In regards with the association, how can we compare a variable X and Y? I'm sure I get this one. You want to?
Or maybe the person who asked the question, you can unmute and elaborate a little bit on.
Yeah, please do. Yeah.
Yeah. So I was referring to the previous slide about the ladder of causation.
Yeah. Sorry, I missed
it. You can
this.
go to that slide. Yeah. So in that, in the first part, so it's like could seeing X change my belief in Y? So like, how can a model answer that question? Like, how would it compare? Like, will it compare the properties of X with the properties of Y? Or can you elaborate on that part?
Do you mean for level 1?
Yeah, from level 1 in the questions part, the third question. Like, how would seeing X change my belief in Y?
I'm not sure I understand the question. Are you asking about the limitations of the first level?
Yeah, so like basically, yeah. So I was like trying to understand like how could like this work? Like how could a model answer a causation model answer a question like this? Like how could seeing X change my belief in Y?
Right. Okay. So you are asking about how to answer questions beyond level 1, I guess.
Yeah. Sorry.
So yeah, I guess the answer is that once you have a causal model, you learn more than just the co-occurrence of some values of those features. You learn really the mechanisms that lead from some input to some output. And so even if you have some conditions that the model is asked about, some conditions that have not been seen in the training data, you can kind of simulate those mechanisms and come up with an answer for those conditions that were never seen before.
I have a question.
Yes, please.
So previously, on one of the slides, you talked about how the IID assumption limits learning and like limits our ability to go to these higher levels of reasoning. So how does data augmentation break the IID assumption? Because if you're just treating the augmented, examples as additional data, you're still maintaining IID, right? Like in theory, you could have just observed those in practice as well. Like the mechanism hasn't changed of the learning though, right?
I don't think that's correct because with the augmentations, you provide examples that might not be the same as the actual distribution of the training data. Say you might have, say you are adding a horizontal flips of images. In the training data, you might have people looking mostly on the right and cars facing to the left. Once you add those data augmentations, you might have as many people looking to the left and to the right, and then cars also, as many of them being to the left or to the right. So you can break some of the biases of the original data distribution.
Yeah, that makes sense. Like that the bias, that it's addressing bias, but how does it address causality, right? Which is what you were discussing on the slide that you have up right now, where you're talking about, X leads to Y leads to, so like a causal chain, right? How does data augmentation address that, or does it not address that?
Yeah, it does, because it provides you information about the mechanism between the X and the Y that is independent from the marginal distribution of the X. So like I said, you might have in the marginal distribution of examples are facing to the left and people to the right. But here with the augmentations, you are providing information about the mechanism between the X and the Y that is not dependent from the original distribution of the X. Say well, you're basically telling the model that the flips between left and right does not matter. It's
okay.
Like,
I understand what you're saying.
Yeah.
So you're saying removing bias and is the same as focusing in on causal relationships, because then you've removed the false causal relationships, right? And now the only ones that remain are the true ones, right?
Yes, right. So that's what I try to explain here with the factorization. So once you have the right causal Bayesian graph, the Bayesian graph that is actually causal, then you have a factorization into mechanisms that are independent from one another. And that is basically disentangling the mechanism that generate the task. So in this case, you are isolating the biases of the data into like the P of Q and P of I, and the mechanisms that are actually relevant for the task are only in the other two conditionals here, sorry. And so those two are the ones that you can still keep to apply at this time, and you don't care about the P of A and the P of Q because that's just the biases of the training data set.
Okay, I see. Thank you.
I have one question.
Yes.
So the data augmentation. So it seems that data augmentation could be a little bit domain related or task specific.
Yeah, absolutely. Yeah.
So how can we generalize that? I mean, if you want to address the problem.
Yeah. That's a good question, and the causal perspective tells you that you cannot do that. That's just the fact that data augmentation has to be task specific because it specifies some invariances over the here, y I denote x and y. It denotes some invariances that have to be specific for the task. You cannot find a data augmentation that is going to be universally good or suitable for the task because it to be useful, it has to tell you some properties. Well, has to tell you something about the properties of the data generating process of the task that you care about. So you cannot find something that is going to be universally good.
So we have to first understand the bias and the problems of the data.
Exactly, yeah. And that's really a point that, well, it's useful once you know that's just a fact of nature. It kind of tells you that it's pointless to try to find a data augmentation that's going to be universally good.
Yeah.
All right, anything else? So I guess I'll go on. So I have another two examples of existing methods that are interesting to look at from a causal perspective. And the other two are a bit more specific to VQA. So this one is about learning from multiple training environments. So it has actually been done in multiple tasks. And I give you some examples here from a data set that's called a BAX data set for domain generalization in image recognition. And what we have here is images with the same set of labels. So you have dogs, horses, persons, and giraffes, and a few more things. But the point is that you have different subsets in the training data. You have examples with paintings, examples with cartoons, with photos, with sketches. And so we have different distribution of the data, basically. And what I'm proposing here is that we can see that from a causal perspective in the sense that it provides information at level 2. So another example of this kind of data in VQA, it's a paper that we had last year, I think. It was called Unshuffling Data for Improved Generalization. And what we did is to use the VQA-CP dataset, which is it provides just one signal training set. But what we did is to cluster the data in this training set into multiple environments. So we basically recovered multiple non-IID subsets of the data, and we showed that this can help generalization. And so the point is that we have different subsets of data that are non-IID, and then there are different methods that can learn a predictor that uses this kind of data. I'm not going to go into the details on how to learn such a predictor. There are multiple ways to do it, and that's not really the point here. The point is that from a causal perspective, by using data from each environment, we actually observe the effect of an intervention on a variable that is a hidden variable, but a variable that is originally spuriously correlated with the labels, but not the direct parent of the labels. And so what we get from each environment is data that is sampled from a different intervention on this variable Z. And so again, that's the point is that we get information from level 2, which is much richer than just one data set of IID data. And so again, it's interesting to pinpoint the root source of the improvements. And here, that is in the knowledge of the factor variations that we use to cluster the data. If we don't have this knowledge, we cannot recover some meaningful non-ID subsets of the data. We have to input some expert knowledge that is task dependent or use some extra annotations like extra labels, or we need something else. It doesn't come out of nothing, but if we have a little bit of knowledge, it can be very powerful. And now a third example, it's also some work that we did last year on VQA and a few other tasks. It's about using counterfactual examples. And here I will show that it provides information at level 3. So what is it exactly? So counterfactual examples, there are basically pairs of training examples that are very similar, but that have different labels. We have examples on NLP tasks. For example, on the right here, we have for settlement classification, a data set of movie reviews that have positive and negative ratings. And so these were collected by asking specifically to the annotators to change a word or a couple of words from one sentence to flip the label. So it was a very specific ask to the annotators, but what we get is those kind of pairs of almost identical examples, but with a different label. Another technique to get this kind of counterfactual examples with images, it's something that we did with images from Coco. We used in painting technique. Actually, we collaborated with other people who provided this kind of images. And I know people at ASU have used similar techniques on VQA with the mutant paper. So by using the existing annotations of objects in the images that are known to be relevant for questions or given labels, we can mask those objects and in paint the region to make the image still look kind of natural. And again, the result is that we have examples that are very similar, but with a different label. And so this has been used before in other works, and using them just as additional training data. So just throwing those new examples in the data and running just as usual. And this was shown to be quite effective, actually more effective than having the same number of traditional or traditionally collected examples. But what the causal perspective tells us here is that the level 3 information is not in the individual examples themselves. The information is really in the relations between the pairs of examples. So the information is in the fact of knowing that between the two examples in the pair, there are only minimal differences. And that tells you that there's something to be exploited in those relations. So we proposed a new training method for neural networks that adds a new loss that aligns the gradient of the decision function with the vector difference between the pairs. So basically between pairs of examples that are known to be counterfactuals of one another, we align the gradient of the function and basically align the decision boundary to be orthogonal to the difference between those two examples. So what we do really is to use information that was there in the data, in this kind of data. The information was there, but it was discarded so far. And we show that we can get much better improvements in generalization, and especially generalization across data sets. And we did that for a few tasks in NLP, in image recognition, and in VQA. And it was pretty impressive, the kind of improvements that we get. And so, yeah, here what's interesting also is to pinpoint the root source of the improvements. And here, that's really basically the annotators that were given those instructions to build counterfactual examples for the movie reviews, or for the images, the annotations and the knowledge of what were relevant regions that could be inpainted or masked. So again, it's something that it's not coming out of nothing. There's really data that you have put in the method, or extra annotations, or some specific knowledge about the task or the kind of data that you have. But then if you can use relevant information, that you can use little of that input to get a lot of benefits. I think I can move on to some takeaways from this talk. I think the one thing to remember, if there's one you can take away, that's there are fundamental limits of what can be learned from ID training examples. And it doesn't matter how much data you have. It's just the fact that this kind of data doesn't have all the information that you need to do OOD generalization. And knowing those principles of causal reasoning are really helpful, because they can tell you why a method just cannot be working, or if you have the actual information that you need to solve the task that you want. But it doesn't tell you how to solve the task. It doesn't tell you how to design methods, really. There's still major open problems. And basically, that's how to do deep learning, that is learning representations at level 2 and 3 from raw high-dimensional data like text and images. We can do a lot of things in causal reasoning if you have predefined discrete variables that you can observe, but extracting representations that you can do some causal reasoning on from high-dimensional data, that's an open problem. And so what I also invite us to do is to really question what our benchmarks are measuring. And we've had, unfortunately, many examples in VQA, but also in other fields, from image recognition to, well, in NLP, there's quite a few, and question answering in general. A lot of data sets have shown that there are biases and issues, and they basically don't measure what they are designed to measure in the first place. And even with some good intentions, like the VQA-CP dataset that has an ROD test set, it seemed like a very good idea, but we had a paper last year that showed basically all the ways in which this dataset had been misused and basically was not fulfilling its initial function. I think that's a question that's always worth keeping in mind. Even if there are established datasets that everybody uses, it's always good every once in a while to question whether this is really the metric or the data that we really care about. And also, something to always try to keep in mind is that we should always strive to get down to the root cause of the improvements that you observe with some given methods. So I think the causal reasoning principles here are very helpful, because they can tell you what is really the information that we need and whether the information is there. So if you have a method that's doing better than another, it can only be better because either there's some inductive bias that's useful, or there's an additional supervisory signal that's being used that wasn't used before. So in the first place, if there's an inductive bias, that means from a causal perspective that it tells you something about the causal structure of the data generating process. And so that means that this inductive bias cannot be universal. That's basically what the no-free-lunch theorems tell you. It has to be specific to the causal structure of the data generating process of the task that you are trying to solve. That means that you have to put some knowledge of the task into designing those inductive biases. Sometimes we do that unknowingly by just trying new architectures and finding stuff that just works for some reason, because we've tried so many of them that it ends up working better. But in the end, if it works better, that's because it gives us a prior over the space of hypothesis function that we optimize over, a prior that gets us closer to the actual structure of the causal structure of the data generating process of the task. So it's not randomly better. It's better for some reason. And if we can pinpoint why it's better, it can also help us figure out what are the limits of applicability of some methods. Why is some method, some architecture better on some task, and what are the other tasks on which it can be better? That's the kind of questions that causal reasoning can help us with. And then for building better models, I think causal reasoning doesn't tell you how to build better models, but it can point in directions. At least it can tell you where to find the information that we didn't have before that could be helpful for improving generalization. So like I said, using data from just level 1 is not enough. But if we have information from level 2 or 3, then we can do better. And that means having data that is non-ID. So what does it mean? For example, it could be temporal data, so non-stationary data. If you observe data over time that is changing because some underlying factor variation, or like the annotators are the different mood at some point, they might produce different questions or anything like that. That's the kind of data that can give you more information than what we had before. Some existing data sets also have some annotations that are unused, some kind of metadata. For example, in many data sets, there are some IDs of the annotators. Sometimes they're, well, very often they're not released, but they are collected. So it's basically the identity of the terpers. So we could use that to get some non-ID subset. For example, people from a certain demographic could produce questions with a different bias than some others. So this is the kind of non-ID subsets of the data that could provide information that we didn't have before. So we could also go beyond the static training and testing phase that we use now. And continuum learning, it's a paradigm that could also get better in a sense that it could use those non-stationarities. So currently continuum learning is mostly about limiting or mitigating the sequential availability of data. But if we had methods that could actually do better with non-ID data, then continuum learning could actually get better than standard learning. And one last thing is that we should always keep an eye out for circular arguments. So if you want to use some additional information, you cannot buy one on stale. For example, if you want to generate counterfactual examples, you do need some input from outside, like an oracle or some additional information, additional data, additional annotations. So you cannot generate counterfactual from one model and also label those examples with the model and then hope that this is gonna improve the model. You need at some point to have some input from the outside. Information doesn't come out of vacuum. And just an application to VQA and vision and language. For example, if you want to have a self-dialoguing agent, like you learn a model that answers questions and a model that generates questions, if you have those models play with one another, they will not get better by themselves. You need to put some knowledge from outside at some point. So it can be something that is actual data from the outside, or it can be some structural constraints, for example, on the data, let's say the language that is used between those two models. This can help, for example, shape and provide some inductive bias on what they learn and kind of teach one another. But you have to put something in to get something out. So I think that's a lot of things already. I guess I'll stop here and I'll be happy to take more questions.
Thank you, Damien, for the great talk. So we are going to open the floor. Also, give us a kind of idea, like when we'll typically open this seminar till 5:45 here. So if you have other obligations and then you need to leave early, please let us know.
No, fine.
Feel free. Okay.
All good.
Maybe I'll start. This is really great takeaways, a lot of them. And at a very higher level, what would you think some of the takeaways are specifically for VQA and vision and language tasks, or are there any takeaways that you are mentioning here are also applicable to tasks even outside of VQA, or be general to other AI tasks, while we are routing from VQA task and coming up with on this set of observations and guidelines, right? So I'm having this fairly general question.
Yeah, I think all of this actually, there's very little in this talk that is specific to VQA. A lot of what I said is just generally applicable. And I think this hasn't come in the mainstream machine learning consciousness yet, because for a long time we have addressed tasks that were close enough to be associative in nature, not to need this kind of generalization outside of the training data distribution. So I think now VQA is one of the tasks where we are really pushing the limits of this kind of approaches. And I think that's why I'm glad to present these ideas here with the people who are working on vision and language, because this is really the far end of the complexity spectrum of what we do in computer vision. So I think that's why it's more and more relevant.
Thanks. Could you elaborate a little bit on the argument of a model cannot generate and annotate its own counterfactual examples? Because I'm trying to think of an example that, well, I understand your argument is basically the model will get into a kind of circular loop and getting worse and worse if he is only using its own generated labels to train itself. But isn't it also part of the argument of transfer learning that part of the data you learned correlations will help you to annotate? I mean, the partial model attending to that part of data helps you to generate or generalize labels to other half or the other part. So are we have? I mean, my feeling is we are seeing maybe the model can generate and annotate to a certain extent, and then it will get into a vicious cycle and going down with the performance. That's my speculation, but I don't have any experimental data to support that.
Yeah, it's a very good point. So you are totally correct. And I think what this perspective tells you is that it gets better so far as you are putting some inductive bias. For example, the fact that the distribution is kind of smooth to a point and then changes, but the improvement is coming out of something. It is coming specifically from the knowledge that you are putting in the method of the fact that it's kind of a smooth function to some point. Another parallel, so you mentioned transfer learning, that's a great one. Another one that I was also thinking about is adversarial training, where you do this kind of counterfactual generation. So you generate basically examples that are close to your training data, but for which you think that the model is wrong. And then you make basically the model smoother around the training example to keep the same label to those kind of nearby examples. And so the knowledge here that you are putting in is that there's some smoothness on the decision function that you think is correct. And that's basically telling that the causal structure and the causal mechanisms of the task are smooth to a point. I think that's my suggestion here, is that we should think about what is the knowledge that we are putting in our methods to make them better. And that can tell you how applicable they are and what are the limits of the improvements that you can expect.
Right. So I thank you. This is really great insight. And I have one last comment. I'm also seeking you comments as well. So I really like your argument saying that whenever we observe improvement, we need to root, right? So pin down where this improvement is coming from. Actually, I think it also applies whenever we see worse performance, we need to root why this performance loss and where is this performance loss coming from, right? A lot of times we're saying like bring knowledge into the model, and bring knowledge into the models a lot of times, rather than improving, may hurt the performance on the current benchmark matrix. But that doesn't mean having that knowledge being introduced to the model is hurting the model, or how to put it, is in general bad idea, right? So we are, for example, if we impose strong knowledge into the model on the current training data, it may not be well reflected. I'm not sure whether you guys also observe such kind of behavior, but doesn't mean that bringing this it's not a good idea, right? Doesn't mean that it's not a good idea. So I really like that comment as well.
Yeah, absolutely. I think the issue here is a problem of the evaluation. So that brings us back to the second part of the talk about evaluating models. The thing is that some of the benchmarks that we use do not evaluate what we really care about. They're evaluating some kind of associative behavior that is linked to some distribution of the data, but they do not evaluate the actual mechanisms that we care about, that is the model using some knowledge and doing some operations on this knowledge and so on. So the problem is that we might make some models better, but they do worse on the benchmarks that we have. And so we cannot discard those ideas, whereas they might have been good ideas, but we just don't have the right way to demonstrate that they have.
Totally agree. So I'm going to open the floor to see if there's any other questions from the audiences as well.
Damien, I have a comment. So when you first started with the causal models, I was actually thinking that the questions that you will be asking will be causal or counterfactual questions. So we actually did some work, ASU, me and one of my students, we just under submission is where we create a data set where we ask questions about like the effect of a particular action. So this, you mentioned about the actions, the do thing, do's are basically actions. So what happens if you do this? So those kind of questions, we had a data set and some models working on it. I guess later we can share with you.
Yeah, I would love to see that.
Yeah, just a comment. Okay.
Yeah, thanks. Yeah, that sounds interesting. Yeah.
Hi, Demi. I have one question. Yeah, thanks for your talk. It's very interesting. So my question is that how do we know that's when the model cannot generalize well on all the data sets? So let's say a model, it performs well on the training sets, but it doesn't perform well on the testing sets. But how can we know that the model didn't perform well on testing set because the testing set is OOD?
So are you asking about how to create the test set that would measure what we care about, or about interpreting the behavior of a model that doesn't do well?
So let me give a bit more concrete example. So
Yes,
in
please.
here, yeah, let's say that VQACP, we know it's OOD. So when the model perform not well on this VQACP, then we will say that this because the model cannot generalize well on OOD data sets. But if we don't know that the testing data set is OOD, it may be, but we don't know. How can we say that the model cannot generalize well on OOD?
Okay, I see what you mean. Yeah. So I think it if you don't know first, if you don't know whether the test set is OOD or what are the differences between the training distribution and the test distribution, then it's probably a bad benchmark in the sense that you don't know what you're measuring really. So for a great, I think VQACP had many limitations, one of them being that it was just one intervention. So it was one different distribution from the training data. And you could be very good on this other one distribution or very bad on this one distribution. It doesn't tell you really the behavior of the model in general outside of the training distribution. So there is a new data set that is kind of similar to VQA-CP. It's called GQA-OOD. So it's based on GQA. I think the authors of that data set did a much better job. So they generated multiple different test sets that were different from the training set. And so if you want to demonstrate that you do really better in OOD generalization, then you have to do better on all of those different distributions. So that's a kind of benchmarks that we have, but for many tasks, we do not have this kind of things.
So I have a related question, Damien. So on the notion of OOD-ness, in, let's say, in image data or like image classification data, it's easier to, at a distributional level, say that these two distributions are at a so-and-so distance from each other. And you can have theory that says, okay, I can generalize within some distance of my distribution. But in VQA, it becomes tricky because you have two modalities and the notion of similarity in language is really messy. So
yeah,
if we want to evaluate on different OODs data sets, how do we get this kind of some kind of principled evaluation there? Like, what is your insights? What are your insights?
Yeah, I think this is hard because you cannot to design a good benchmark, you have to put in also some task specific information in the design. So that's basically dependent of what I showed with the 3 levels. So having a model for the higher levels requires more information for the training, but it's the same for the testing. If you want a model that tests for level 2 or a model that tests for level 3, it takes also much more information from the annotators or the benchmark designer to design those things. And so if you, for example, for VQA, if you want to do interventions, you have interventions to generate different distributions. You have many things to choose from. What do you intervene on? Is it distribution of the questions, of the images, on the joint biases or whatever you call them. There are many things you can do, and you cannot have an automatic algorithm that's going to turn an IID training set into a level 2 benchmark. That's the key. Yeah. So I don't have a good answer. I'm just telling you that yes, this is hard.
Yeah.
Yeah, and it has to be task specific. That's the point, I guess.
And on a similar note, like you had an example where I think you removed a book from an image. But I think that was an example of a counterfactual image. But in some cases, maybe, especially in VQA, if you remove objects, or substitute words, the correct label is usually ambiguous. Not usually in many cases. So how do we account for that?
Yeah, absolutely. So ideally, you would like to generate those examples from real data. Like you would take a picture of the question, for the question with the book, and then you would remove the book from the image and take the same picture. And you would have annotators writing questions that are relevant in one image and also still relevant in the other. So that would be extremely expensive, but that would be the right way to do it, because what you care about is like I said, is the data generating process. That's the annotator that's like asking and answering the questions. That's what you want to mimic in the model. And so that's what should be used ideally to generate those counterfactual test examples. So here we use some heuristic to get kind of close to that with a much easier, much cheaper way, but that's really not ideal. It's just a heuristic, and yeah, that's not the other ideal case.
Actually, that might also bring in the temporal aspect if you make changes sequentially.
Yeah, So I think it's worth thinking about annotations that exist in existing data sets that could be used to generate those benchmarks. So like I said, there's information in those data sets that could be used to build better models, but this same information can be used to build better benchmarks, kind of level 2, level 3 benchmarks.
Damien, so like the counterfactual reasoning that like Pearl or what it discusses is somewhat like different. Like the way you are using counterfactual is more like negation of the like a particular fact, or the example you gave. So it's like you have the negation. What Pearl uses counterfactual is in the sense that it's like something you observed, and I mean it's a counter to what you had initially in the model. Slightly different from negation, and it's more about like the reasoning about some particular action that you did. Or let me give you an example. Like in the literature, in the philosophy literature, they would say, if say Kennedy had not died, would this have happened? So it's like we know Kennedy was murdered. If he wasn't murdered, would this have happened? So it's a kind of a slightly different kind of a thing. I think what you have is at more like a negation of the particular statement. Or
yeah, so it's a special case really of counterfactual. So the definition of a counterfactual really, it's an intervention where you actually keep the stochastic factors of variations constant. So say if you have an image with a question that gives a certain answer, you have some exogenous variable that define what is in the image and what is like the writing style of the question and some extra words and so on in the question. And so when you have a counterfactual example, you keep all of those stochastic factors, those exogenous variables to the same value. So you keep like all the background of the image, the style of the question, all of that, you keep that relevant, and you only do an intervention of one specific piece of the data generating process. Say you change, like you remove the book in the image, or you change one word of the question, but everything else stay the same. So that's why it's also called counterfactual.
Is the same. The unrelated thing stays the same. Like when you so if you like if when you change something that like if you look at the causal graphs, so if you change a particular thing, then all the incoming arcs that are coming, you kind of cut it out.
Yeah, for one piece, one very small specific piece. Yeah.
Right. So those parts remain the same. The one that is cut up, but the one below, the effects, they will change. So
yes, right. And well, the key thing for the counterfactual is that the exogenous variables that are not represented in the graph. So for each node, some stochastic input that come into the causal mechanism, this specific factor stay the same in the counterfactuals. I guess that's the.
Yeah, again, we can discuss later more.
Yeah, I would love to. Yeah. Thanks for your comments. Yeah, I think
this is my AI class. The Pearl's counterfactuals, causality, all of those things I teach in my AI class.
Great. Yeah.
So we can talk more.
Yeah, great. Thanks.
Thank you, Damien. We really hope that in a near future or in the next year or so, we can have an in-person meeting and we'll catch up somewhere in
Let's
this
hope so.
world.
Yeah.
And good luck with your move. And I just realized you are moving to Switzerland. Enjoy the snow there.
Very soon. Yeah. If I can travel, yeah. Let's see how it goes.
Okay, I see.
Yeah. But yeah, it should happen soon. Yeah, soon enough.
Yeah, please do visit us after the move, after things become normal.
Yeah, I would love to. Yeah. Thanks again for having me, Dan.
Thank you so much. Have a nice day. Bye-bye.